the focus of this lesson is on finding all the complex zeros of our polynomial p of x. And the process that we use is similar to the process that we use for finding all real zeros. We're going to find the possible rational zeros as our first step. We're going to use Descartes' Rule of Signs to determine the number of positive and the number of negative zeros. Then we're going to do our upper bound and lower bound testing using synthetic division while simultaneously finding the zeros. The reason this differs from finding all the real zeros is just at the end when we do our quadratic formula to solve for our remaining two zeros, it's possible that they come out to be complex or imaginary as opposed to real. And so let's go ahead and just kind of go through our steps. So again, our initial step is finding our possible rational zeros. So I'm just going to write that down. And just remember, you find the factors of your constant and then the factors of your leading coefficient, and then you divide those off from each other. And we call those sets P and set Q. So our set P is all the positive and negative factors of 13, which are just 1 and 13. Our set Q is all the positive and negative factors of 1, which is just 1. And then our possible rational zeros is all our P's over Q. And if we do that, we would just come up with 1 over 1, which is 1, and 13 over 1, which is 13. So these are our possible rational zeros. So this is where we'll start with all our synthetic division. And the next thing we're going to do as our step 2 is find the possible number of positive zeros, and then we'll find the possible number of negative zeros. So the possible number of positive zeros, if you recall, is based off of our p of x, its signs. So I'm just going to go ahead and take p of x and make sure that it is written in descending order, which it is, and I'm just going to list the signs of all of the coefficients and constant. And what we're trying to do is count the number of variations of signs, so where we change from negative to positive or positive to negative. And we could see that we have a count of 2. So that means there's 2 possible positive zeros, or we keep subtracting off 2 till we can't. If we subtract off 2, we would get 0. There could be 0 possible positive zeros. If we want to consider the possible number of negative zeros, we're going to look at p of negative x. So we'll take our function p and evaluate it at negative x. And when we do that, we could go ahead and just write that down, but it'll be negative x cubed minus 5 times negative x squared plus 7 times negative x plus 13. A negative x to the third is negative overall. A negative to the second is positive times this negative is negative. A negative times a positive is negative, and then that constant had a positive sign. So we can see that we have one variation of sign. And then if we subtract off 2 from 1, that brings us down to negative. So that's not useful. So that's our only possibility for the possible number of negative zeros is 1. So then moving on from there, we'll go ahead and do our upper bound testing. And so with our upper bound testing, we're going to focus on the positives. So if we focus on the positive rational zeros that we had, our focus is going to be on 1 and 13. And we want those in order from smallest to largest, which we have. And we'll start off with our synthetic division on 1. We'll use the coefficients of our polynomial, which are 1, negative 5, 7, and 13. And then we'll go ahead and carry out the synthetic division, multiply, combine, multiply, combine, multiply, combine. And we can see that this is 1 is not an upper bound because we don't have a row of all positives, and 1 is not a 0, and the reason we know it's not a 0 is the remainder isn't 0. So then we're going to go ahead and move on and try 13 with the same coefficients since we haven't found any zeros yet. And so we'll pull down that 1, multiply, combine, multiply, combine, and then multiply, which ends up being 1443. So let me go ahead and write that in. And then you go ahead and combine, which when you combine you'll get 1456. So it technically doesn't matter what this number is. We could see it was going positive, but this is all positive. So 13 is the upper bound, but we did not. 13 is not a 0. So then what we'll do is we'll go ahead and move on to our lower bound testing. And with our lower bound testing, we're going to use our negatives. So we'll use -1 and -13. So we'll start off with -1 because you actually start with the highest negative, which is still the same order as far as the numbers are concerned. And we're going to keep using our coefficients because we haven't found any zeros yet, so no depressed equation yet. And bring down that leading term, multiply, combine, multiply, combine. And we see that -1 is a 0. And if -1 is a 0, that means x minus a -1 or x plus 1 is a factor. And we also see that -1 is a lower bound because we're alternating signs. You have a negative, or you have a positive, negative, positive, and then 0 could take on a negative. So -1 is a lower bound as well. So we won't have to test -13 because it can't be a 0. And then what we can do from here is that means that the factor x plus 1 divided into our original polynomial x cubed minus 5x squared plus 7x plus 13 and gave us the depressed equation 1x to the second minus 6x plus 13, which I get from that last row of my synthetic division, and it's going to be 1 degree less than my polynomial. And so this is a quadratic. So then all we have to do from here is we could use our quadratic formula. So our a is 1, our b is -6, and our c is 13. And we'll perform a quadratic formula to get our remaining 2 zeros that we would have. So the opposite of b plus or minus b squared, which is 36, minus 4 times a times c, all over 2 times a. But simplify that, you get 6 plus or minus the square root of 36 minus 52 all over 2. But that's just 6 plus or minus the square root of -16 all over 2. And this is where we get into the complex zeros because you're taking a square root of a negative. And so when that happens, the square root of a -1 is I, so I will come out from the fact that you took the square root of that negative piece, and then the square root of 16 is 4, so it's 4i, and then all over 2, and then since 6 and 4 are both divisible by 2, we'll go ahead and divide that out. 6 divided by 2 is 3, and 4i divided by 2 is 2i. And so at the end of the day, we can see that our zeros are -1, which we got from our synthetic division, and then 3 plus 2i, and 3 minus 2i. And that completes our problem, because we can see we're degree 3, so we're not going to have any more than 3 zeros. So those are our 3 complex zeros. Notice that we have 1 negative 0, like our Descartes Rule of Signs said we would have, and we have 0 positive zeros because we have 2 actually imaginary complex zeros. So